So we introduced the law of quadratic reciprocity last time, and today I want to go through a proof. There is no quick and easy proof of it, but the one I'm going to go through is a proof of Gauss, which uses something called Gauss's lemma. I consider it to be one of the most elementary proofs. So we'll first of all state the law of quadratic reciprocity again. Then as background, we'll need some properties of the greatest integer function. We'll state Gauss's lemma for evaluating the Legendre symbol. As a special case of that, we'll evaluate when 2 is a quadratic residue mod p. Then we'll prove the key lemma for quadratic reciprocity, and then finally complete the proof. So again, if p and q are odd primes, then p over q equals q over p, unless both primes happen to be congruent to 3 mod 4, in which case they have opposite signs. And we have this equivalent formulation like this that we won't need to make use of today. So first of all, what is this theorem really saying? Let's consider the following example. 3 over 1009 and 1009 over 3. So the first symbol is asking whether 3 is a perfect square mod 1009. So we are studying this congruence. X squared congruent to 3 mod 1009. And so we're working in the finite field Z mod 1009, a field with 1009 elements, and we want to know, is 3 in the subgroup of squares? For the second symbol, right here, we need to study x squared congruent to 1009 mod 3. And so you're working in a much smaller field, in Z mod 3. Now if I was going to ask you which of these two congruences is easier to address, what would your answer be? Well, it's much easier to work in a field with 3 elements than in a field with 1009 elements. In fact, 1009 is congruent to 1 mod 3. So I can just reduce this one. And plainly, there are solutions. This has solutions, x equals plus or minus 1, and therefore 1009 over 3 is equal to plus 1. It is a perfect square. Now the remarkable thing is, knowing this information tells us, therefore, by quadratic reciprocity, just call it QR, the symbol where I put 3 up on top and 1009 down below is also plus 1, because 1009 happens to be congruent to 1 mod 4, and these two values have to agree. So knowing this simple fact, that 1 is a perfect square mod 3, tells us that 3 is a perfect square mod 1009. A remarkable fact. So for background, let's review the greatest integer function, square bracket x, which is defined for any integer, any real number x. So property 1, if you take square bracket of x plus n, where n is an integer, this is just bracket x plus n, a very elementary fact. Property 2, square bracket of minus x is given by this formula here. And then property 3, if I have an interval of real numbers with non-integer endpoints, then the number of integers in the interval is bracket beta minus bracket alpha. So for the proof of part 1, so let x be some real number. Then you can write x as its greatest integer part, bracket x, plus a tiny number strictly less than 1. Let's just call it an epsilon here. That's just the definition of the square bracket symbol. And so if I add an integer n to it, so n is an integer, then this would just be bracket x plus epsilon plus n, which is this integer plus epsilon. And therefore this is the greatest integer part of x plus n. In property 2, I want to evaluate bracket minus x. And we'll just do a proof by picture. You can write down a formal proof. Here's 0. Here's x. There's minus x. Right here would be bracket x. And right here, so it's right there, would be minus bracket x. And now where is bracket of minus x? Well, bracket of minus x is the integer less than or equal. It's sitting right there. And so we come up with the formula that bracket minus x, in general, you would take minus bracket x, and I'd have to move left 1 unit to get to it, unless x happens to be an integer. And if x is an integer, this would just come out to be equality. And then finally, counting the number of integers in an interval where alpha and beta are not elements of the integers. That should be a z right here. So here's alpha. Here's beta. Right here is bracket alpha, greatest integer. And right here is bracket beta. And so I want to count the number of integers in this interval. So alpha is not in the integer, so there's a gap right here. Bracket alpha is strictly smaller than alpha. So the first integer in here is right here, bracket alpha plus 1, and then you have bracket alpha plus 2, and this is the biggest integer in the interval, which would be, which is what? Well, you have to add what? Think of this as bracket alpha plus bracket beta minus bracket alpha. So the number of integers I'm spotting in this interval is exactly this quantity right here. Gauss's lemma. Let P be an odd prime, A be an integer not divisible by P. Consider the set of multiples of A going from 1A to P minus 1 over 2A, and then reduce them mod P to a value between negative P over 2 and plus P over 2. So you have a complete residue system mod P that runs from minus P over 2 to plus P over 2, and you've reduced each of these values to one of those integers. I'll let nu be the number of negative values in the resulting set. And the claim is the Legendre symbol A over P is just negative 1 to the nu power. Thus, the value of the Legendre symbol depends only on the parity of nu. So knowing the value on the right-hand side, we just need to know, is nu even, in which case it's a plus 1, or is nu odd? Proof of Gauss's lemma. So let's say that L1A through L nu A are the multiples that are congruent to negative values, and that the remaining multiples are all congruent to positive values. So I claim the following. if you form the set where you take the minus of these new values here, so minus L1 of A through minus L new of A, and then I put that together with all of these multiples of A, that this forms all of the values from 1 to P minus 1 over 2. So remember, these values right here are congruent to some number between negative P over 2 and negative 1, and so when you take the opposite, there'll be values between 1 and P over 2. So all of these values are between 1 and P over 2. And the question is whether we get any duplication. So note, there are P minus 1 over 2 values listed. And they're all members all elements of the set 1, 2 through P minus 1 over 2. So we just have to show they're distinct. So the only way you could have duplication, certainly none of these are all distinct right here from one another, because the L sub I values are distinct mod P, and these are all distinct from one another. So the only thing we have to wonder is whether one of the negative values could be the same as one of the positive values. So suppose a minus L sub IA was congruent to an L sub JA mod P. So suppose this happens. That would imply that LJ plus LIA is congruent to 0 mod P, which would mean that P is a divisor of LJ plus LI, since A is relatively prime to P. Well, how big is Li plus Lj? These values are going from 1 to P minus 1 over 2. So 0 is less than Lj plus Li, and that's less than or equal to P minus 1 over 2 plus P minus 1 over 2, which is P minus 1. So how is it possible to have P, a divisor of Lj plus Li, and at the same time Lj plus Li be a number between 0 and P minus 1? That's a contradiction. Therefore, you can't have any such thing, and we've shown that these values are, in fact, distinct and fill up this entire set. So what does that do for us? This is very much like Wilson's theorem. Well, it means if I took the product of the numbers listed on the left, it'll be the same as the product of the numbers listed on the right. So when you take negative 1 L1A times minus 1 L2A times minus L new A and then you go L new plus 1A L P minus 1 over 2A, so those are all the distinct multiples. That has to be the same as multiplying 1 times 2 times 3 times P minus 1 over 2. mod p. Now on the left-hand side, I see new terms that have negative ones. Then we have a power of a. And how many a's are there? Well, every term here has an a, so that's a to the p minus 1 over 2. Then we have a product of the li's. Congruent to p minus 1 over 2 factorial. Now, what are these values? The li's run through 1, 2, 3, 4 up to p minus 1 over 2. So that also is just p minus 1 over 2 factorial in a permuted order. Aha! We can now cancel p minus 1 over 2 factorial, since it'll be relatively prime to p on both sides. So I cancel this, and I cancel that, and I'm just left with negative 1 to the new power times a to the p minus 1 over 2 is congruent to 1 mod p. But now the Euler criterion tells us, aha, this is Legendre symbol. So you got negative 1 to the new times the Legendre symbol is 1. And since this value is plus 1 or negative 1, I can just put it onto the other side, and I would get AP is congruent to negative 1 to the new mod P. QED. So we have a formula for evaluating the Legendre symbol using the value nu. Next, we want to obtain a formula for the value nu. So let a be a positive integer, p be an odd prime not dividing a. So I want to calculate the value nu here. So the lemma says this: you have to count the number of values a, 2a, 3a, up to p minus 1 over 2a, that when you reduce them mod p, belong to the interval from minus p over 2 to 0. Okay, now these are actually positive integers we're looking at right here. So that means if under reduction they're between minus p over 2 and 0, that the actual integer values have to belong to one of these intervals, between p over 2 and p, 3/2 p and 2p, 5/2 p and 3p. So these are the intervals where when you reduce them, they become negative. And how far do you have to go? Well, you have to go up until you account for this biggest multiple right here. And that means you have to let b satisfy this, that p minus 1 over 2a should be less than b plus 1/2 p. So I don't want to include the next one. And p plus 1 over 2a should be greater than bp. And you can find such a value of b just by taking square bracket of a over 2. And I'll let you, you can just do that calculation yourself and verify that we only need to let b run up to a over 2. In that case, notice that this is of the order a times p over 2, which is exactly the order of magnitude we have here, a times p over 2. So by choosing b in this manner, nu is just the number of multiples of a in one of the intervals listed above. And note, these intervals are of this form. You have one of these half type of integers here, j minus 1/2 p, comma jp, where j is running from 1 to b. So when j equals 1, you have a half p, and when j equals b, we get the final interval right here, b minus 1/2 p, bp. So our task is to count the number of values of k, so the number of multiples of ka, such that k times a is an element of one of these types of intervals, where j runs from 1 to b. This is equivalent to counting the number of integers k belonging to one of these types of intervals. So I just divide both sides by a, and you get j minus 1/2 times p over a, comma, j times p over a. So we're just counting the number of integer points in intervals where neither endpoint is an integer. So make a note of that. The endpoints are not in Z. So, what does that do for us? Well, that was one of the first properties of the greatest integer function we studied. Tells us the number of integers in this interval is the square bracket of the right endpoint. So come down to this formula right here, square bracket jp over a, minus the square bracket of the left endpoint. So the value of nu occurring in Gauss's lemma, I just want to sum the number of integers in these intervals as j runs from 1 to b. And so we've established this lemma right here. The value nu occurring in Gauss's lemma is the sum of this quantity right here. Now remember, we only want the parity of nu, whether it's an even or odd number. Okay, before we proceed with reciprocity, let's just do one quick example. Let's determine when 2 is a quadratic residue. And I claim we have the following, that 2 over p will be plus 1 when p is plus or minus 1 mod 8, and it's negative 1 if p is congruent to plus or minus 3 mod 8. And there happens to be this cute little formula that captures that information, and I'll let you go ahead and verify that. It's straightforward. So it basically says that p squared minus 1 over 8 is even if and only if you're in this first case here. So how do we get the formula? So the value nu in Gauss's lemma, we just saw is this sum right here. So in this problem, a is 2. So if a is 2, then b is bracket 2 over 2, which is 1. And so nu, well, that's pretty easy to calculate. J goes from 1 to 1, so j is just equal to 1. You have p over 2, that's a, minus bracket 1/2 p over 2. So bracket p over 2 minus bracket p over 4. And so all I do is I say, okay, what does this equal mod 2? So suppose p is of this form k plus 8t, with k being a member of 1, 3, 5, or 7. So every odd prime is of this form. T is an integer. Then bracket p over 2 minus bracket p over 4. And I just want it mod 2, remember. So that would be k over 2 plus some even number, 4t. And this is k over 4 plus an even number. So these even numbers you can pull out of the brackets, and eliminate when you're working mod 2. So this is just bracket k over 2 minus bracket k over 4 mod 2. And so we just plug in when k is 1, what do you get? When k is 1, you get 0 minus 0, which is 0. You plug in k equaling 3, and you get 1 minus 0, which is 1, for k equaling 3. Plug in k equaling 5, and you get 2 minus 1, which is 1. So we get 1 for k equaling 3 and 5. And then finally for k equaling 7, you'd have 7 halves, which is 3, minus 1 is 2, which is 0 mod 2. And that accounts for all of these cases. So 1 and 7 is plus or minus 1 there. In your homework, you can do a related result, determining when 3 is a perfect square just by applying the formula for nu we saw. And you'll come up with this result. It's a quadratic residue when p is plus or minus 1 mod 12, and it's a non-residue when p is plus or minus 5 mod 12. And these two cases suggest that the value of the Legendre symbol depends only on the value of p mod 4 times a. So think of 12 as being 4 times 3. In the case of 2 over p, it is 4 times 2, and so it depended on the value mod 8. And it turns out that this type of phenomena holds in general. So we're going to get the following lemma, which I consider the key lemma for proving quadratic reciprocity, that a be a positive integer, p and q be odd primes with p not a divisor of a and q not a divisor of a. If p and q are the same value mod 4a, then a over p equals a over q. So the value of a over p depends only on the residue class of p mod 4a. And we are already seeing reciprocity going on here. So we're trying to calculate what is a over p, and we're saying, it only depends on the value of the bottom mod the top. Whereas normally you think of a over p as depending on the value of the top mod the bottom. So this is generalizing what we've seen for the case where a is 2 and the case where a is 3. Okay, proof. Let's recall that Gauss's lemma says a over p is negative 1 to the nu power. And then we saw this formula that nu can be calculated by just summing this greatest integer quantity right here. Likewise, a over q is negative 1 to the nu prime, where nu prime is this sum. And the claim is that these two quantities are equal. Must show same value. Well, same value means what? We're only interested in the even and oddness, because nu is up in the exponent here. Same value mod 2. Let's say p equals plus or minus q plus 4at for some integer t. So p is congruent to plus or minus q mod 4a, remember. Then we've got this formula for nu, and so I'll just substitute in that what p equals here. J equals 1 to b. J, so I have plus or minus q plus 4at all over a there, minus j minus 1/2 plus or minus q plus 4at all over a there equals, okay, so I'll get this plus or minus jq over a, and look what happens on this other term. So put parentheses there. The a's will cancel, and you're going to be left with an even number. So I really don't need to pay any attention to it, because we're only going to be doing this mod 2. And here we've got plus or minus j minus 1/2 q over a. Again, we'll have this even number coming out. So you'll have, let's write it as 2j minus 1 over 2 for t, and then the 2 cancels there. And so mod 2 you'll have plus or minus jq over a and minus plus or minus j minus 1/2 q over a, right? Because this is an even whole number, you pull it out of the bracket and then cancel it mod 2. Likewise with this term right here. So, well, that looks familiar. This, if we didn't have the negative sign, so let's do 2 cases. The plus case, this would be exactly the formula for nu prime, right? The nu prime formula is exactly looking like this with q in place of a. So we're done. We got nu is congruent to nu prime. In the minus case, we use another formula from the first lemma that says square bracket of minus is minus the bracket plus, well, minus the bracket minus a 1. So you're going to get the opposite. Well, the opposite of any number mod 2 is just itself. That's jq over a. It's an a down on the bottom there. Minus 1. And then this one, you'll have bracket j minus 1/2 q over a minus 1 mod 2. But look what happens then. You'll have a negative 1 plus a 1. Those terms, I better use a different color, are going to cancel out, and again we get nu prime coming out here. QED. So in both cases we're getting nu prime. So we're now ready to prove the law of quadratic reciprocity. So let P and Q be odd primes, and we're going to break it into 2 cases. Case 1. Suppose P is congruent to Q mod 4. So let's say that P equals Q plus 4t for some integer t. Then what? Well, let's just calculate P over Q. So P over Q is then Q plus 4t over Q. Now the Legendre symbol, I only need the value of the top mod Q, so that's just 4t. It's a multiplicative symbol. And 4 is a perfect square. So 4 over Q is just 1. Okay, so there's P over Q. Now let's calculate Q over P. Well, Q is P minus 4T. And this is just minus 4T. So this time the 4 over P goes away. You'll have negative 1 over P, and then T over P. Well, what did our key lemma say? Our key lemma says that if P and Q have the same value, mod 4 times the top component, then the Legendre symbols are equal. Well, P is congruent to Q mod 4T. So this is just equal to negative 1P times TQ, since P is congruent to Q mod 4T by our previous lemma. That's what I was calling the key lemma there. So the key lemma really is another form of stating quadratic reciprocity. So, what did we just prove? So TQ is P over Q. So this part right here becomes P over Q, and we see that P over Q is Q over P times this negative 1. Oops, let's go state it again. So I've got that Q over P and P over Q differ by this thing right here. And that's exactly what we want, because what is this quantity? This quantity is plus 1 or negative 1. So this would be Q over P if P is 1 mod 4. And remember, I'm assuming P is congruent to Q, so that would mean both P and Q are 1 mod 4. And it's negative Q over P if both P and Q are congruent to 3 mod 4. Okay, so we've seen that evaluation. That's the negative 1 over P symbol we did early on. 2. Suppose P is congruent to minus Q mod 4. So let's say that P is minus Q plus 4T. Then P over Q would equal minus Q plus 4T over Q, which is 4T over Q, and we get T over Q. While Q over P, so Q, solving for Q in this equation, is minus P plus 4T over P, and that's just 4T over P, which is T over P. And again, relying on the key lemma, now P is congruent to minus Q mod 4T. So by the key lemma, these two quantities, are the same. TQ equals TP. Therefore, PQ equals QP. And we are done. So this is the case where maybe P is 1 mod 4 and Q is 3 mod 4, or P is 3 mod 4 and Q is 1 mod 4. So in those cases, we always get equality here. So as an example, let's just calculate a couple Legendre symbols. So 7 over 1009. So 1009 is a prime that's congruent to 1 mod 8. And so I can flip this because it's congruent to 1 mod 4 without introducing any negative sign. And then I just calculate the residue class of 1009 mod 7. That happens to be 1. You can carry out that division. And so that's trivially equal to 1. Or calculate 86 over 1117. So this is a prime. I'll give you that. Likewise, 1009 is a prime. And it's congruent to 5 mod 8. So it's congruent to 1 mod 4. And so again, we can flip it. But we can only flip when the top is a prime. So I first factor the 86 as 2 times 43. And we'll go into this in a lot more detail in the next section, evaluating the Legendre symbols. I just wanted to do a quick application of reciprocity right now. So I use the multiplicative property. Now 1117 is 5 mod 8, and so 2 is not a quadratic residue. This is a negative 1. 43 and 1117 are both primes. And this is congruent to 1 mod 4, so we can flip it without introducing a negative sign. And then I reduce 1117, and it comes out to be 42 mod 43. And then finally 42 I just view as a negative 1. So minus 1, negative 1, and 43 is 3 mod 4, so this is another negative 1. And so it comes out to be a plus 1 in the end. So 86 is in fact a quadratic residue mod 1117.